A very good morning to all of you. Today we start with the first module of the course Physics for class 12, and the first module is electrostatics. Electrostatics forms a part of a larger area of physics called electromagnetics. So, electromagnetics involves study of electric and magnetic fields. Okay, we will start with some experiments in electrostatics. Some of you may have carried out similar experiments at home, but those of you who have not, I urge you to try out some of these experiments to see the excitement in physics. So, I will start with a pair of straws here. There is one straw here, then another straw in my hand, and what I am going to do is I have a woolen scarf which I will use to rub this straw. I rub the straw a couple of times, leave it. I take another straw here and rub this a few times, and then I want to see what effect it has. You see, it's not even allowing it to touch, it's pushing the straw. So much repulsion is there. You also notice that there is nothing connecting this straw and this straw. There is no string, there is no object, there is nothing connecting these two straws, but this straw seems to be pushing it. What is happening? Why is this pushing that? In fact, the straw, if I take to the other, why is this straw pushing the straw without any apparent connection between these two? Let me similarly take a glass rod and rub with silk a few times and take it near the same surface. You see, it gets attracted. This particular one repelled it, it's repelling it, this one is attracting it. So, it seems there are, and this is getting attracted even without my touching. I put close to the straw, it gets attracted. So, let me charge it again. Here it's getting attracted. So, there seems to be two kinds of forces, one which is repulsive between this straw and this straw is repulsive, and another one which is attractive between this glass which is swiped by silk and this straw. So, these experiments of attraction and repulsion were carried out long ago, and this study of these effects is what electrostatics will consist of. Now, you may have done this experiments at home. For example, if you rub this and take it near some pieces of paper here, you see they are all getting attracted completely. You may have seen this as effects on a comb. If you comb your hair on a dry day, they attract paper, they attract all other kinds of objects here. In fact, I can take this to a metal cylinder and it attracts a metal. See, I am not even touching the metal cylinder, it is attracting and moving the metal cylinder. So, what is this force? What is happening even if I do not have any contact between these two objects? In fact, these are called the electrical effects. You may have noticed magnets at some stage of your life, and here are a pair of magnets. As you can see here, this magnet attracts another piece, another magnet here very strongly. In fact, if you have a metal clip, clip gets attracted by the magnet. So, there are two kinds of effects that you see here. One is between metals, which is a different kind of effect, magnetic effect, and one which is the charging effect, which we have discussed here. So, all these effects constitute the general field of electromagnetism, and in the first module what we will discuss is electrostatics. So, having seen some interesting demonstrations of electric and magnetic effects, we will now start to study the subject in more detail, look at forces between charges, why, what are the repulsive forces, what are attractive forces, and so on. As I mentioned before, this forms a very important part of the subject of electromagnetics, which which is one of the strongest forces in nature. It dominates all atomic forces. It dominates forces which make atoms, atoms making molecules, molecules making solids. All these forces which are responsible are all electromagnetic in character. So, what we saw was, if you rub wool with that plastic, and if you take two such rubbed plastic rods, they seem to repel each other. So, what we say is the plastic rods are getting charged. Similarly, I showed that if I rub glass with silk, then it seems to attract the plastic rod. So, there seems to be two kinds of forces, one which is repulsive in character, the other is attractive in character. So, the science of electricity and magnetism started way back in 600 BC, when Greeks observed that rubbing amber with wool can attract objects. In fact, electron has come from a Greek word which is electron, which means amber in Greek. So, the science of electricity and magnetism, since that time of observation of these forces, developed for centuries until 1820 or so, when Hans Christian Ørsted showed that electric forces, electric charge current, can generate forces on magnetic needles. And then beyond that point, many scientists, including Michael Faraday, James Clerk Maxwell, integrated the fields of electricity and magnetism, and we now have what the field is called electromagnetics. So, to explain the presence of two kinds of forces, repulsive and attractive forces, it seems that there are two kinds of charges. Benjamin Franklin called them by the name negative and positive. In fact, he could have given any pair of names to these charges, but he called them negative and positive. And we must remember, in the negative charge there is nothing negative about it, it is just a nomenclature. And what I showed in their experiment are the following effects, that when the two objects repel each other, that is because both of them have a similar charge. So, what we observe is negative charges repel negative charges. It so happens that positive charges also repel other positive charges. And we also saw an attractive force, and that is because positive charges attract negative charges. So, this charge is actually a fundamental attribute of the particle, just like mass is a fundamental attribute. Now, if you contrast this with gravitational attraction, gravitational force, gravitational force is always attractive. Because there is only one kind of mass, and mass attracts another mass. While in the attribute of charges, there are two kinds of charges, positive charges, negative charges. So, positive charges attract negative charges attract positive charges, but if you have a positive charge and another positive charge, they will repel each other. If you have a negative charge and another negative charge, they will repel each other. Now, atoms consist of these positive and negative charges. In fact, atoms are made up of primarily electrons, protons and neutrons. The protons and neutrons form the nucleus and occupy a distance of about 10 to the power minus 15 meters. That is the nucleus. So, all the protons and neutrons are sitting within this volume, and then the electrons are actually surrounding this nucleus to a radius of about 10 to the minus 10 meters. So, you have the nucleus consisting of electrons, sorry, protons and neutrons, and you have the electrons surrounding this nucleus, and the atoms, the neutral atoms, have exactly the same number of electrons and protons. So, the net charge of a neutral atom is 0, because the electrons and protons have exactly the same charge. To experimental verification now, both of them have exactly the same charge. So, the number of electrons being equal to the number of protons in an atom, the atom is usually neutral. Of course, you can have situations where you can remove an electron from an atom and the atom can get positively charged, because it will have an excess of positive charge compared to negative charge. So, you can ionize the atom, you can have an atom which is not neutral, and you call these ions. Now, charges have very important properties. So, let us look at some of the properties of charge. The first one is conservation of charge. What this implies is total charge, which is the sum of positive and negative charges, in an isolated system is constant. So, isolated means you do not allow any charge to enter from outside, it is completely isolated. So, the total charge of this isolated system is a constant. Now, it does not mean that you cannot generate charges inside, but whenever you generate a negative charge inside the volume, you will also generate a corresponding positive charge. So, there are effects taking place in nature in which gamma radiation can split into a pair of electron positron pairs. One is a positively charged particle, the other is a negatively charged particle. So, the total charge within that volume is remaining the same, and this particular conservation law of charge is an experimentally valid fact. The second one is quantization of charge. Now, this is electric charge is always found in integral multiples of a basic unit of charge. Which we will call E by the letter small e. This is actually the charge on the electron. E is the charge on the electron. E is the magnitude of the charge on the electron, and it is also the charge on the proton. And the value of E is known to be 1.602 1766208 into 10 to the minus 19 Coulomb. This is a unit. C represents a unit which we will again come across later, called the Coulomb, and this is named after the scientist Charles Augustin de Coulomb. And so this is usually approximated as 1.6 10 to the minus 19 Coulomb. Now, this is an experimentally verified fact that whatever charge you find anywhere is always an integral multiple of this number. You cannot have a charge, for example, of 3.01 10 to the minus 19 Coulomb. It is not possible. All charges will be integral multiple of this charge. Now, this charge is a very, very small number. So, just to give you a feel for this number, if you take a 1 centimeter cube of copper, the metal copper, the number of electrons and hence protons is about 2.4 into 10 to the power 24. So, 10 raised to the power 24 is 1 followed by 24 zeros. It is a huge, huge number, and there are so many electrons within the volume of copper, and for each electron you have a proton inside copper. If you take a standard bulb, for example, in which you are passing current and you are getting light, in 1 second about 10 to the power 19 electrons are crossing. So, the electron charge is a very, very small quantity of charge. If you look at matter, if there are so many charges, so many numbers of charges, that usually, unless you are doing some very critical experiments at microscopic levels, it will look as if the charge is continuous. It will look as if you can obtain any charge, but we must remember that charge is a quantized quantity, and the total charge in any system has to be an integral multiple of the basic unit of charge, which is approximately 1.6 into 10 to the power minus 19 coulombs. Now, charges also follow principle of additivity. So, I will, for example, the charge on an electron will be minus 1.6 10 to the minus 19 Coulomb, and the charge on a proton is plus 1.6 10 to the minus 19 Coulomb. So, if you have a certain number of electrons and a certain number of protons, you have n1 electrons and n1 n2 protons, total charge is n2 minus n1 into 1.6 into 10 to the power minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add the charges. 1.6 10 to the minus 19 Coulomb. So, you algebraically add So, if n1 is equal to n2 like in a neutral atom, the net charge on the atom is precisely 0. Now, we will see as we progress that there are different kinds of materials called conductors and insulators broadly. So, what are conductors? Conductors are those materials which allow free flow of electrical current. In these materials, there are electrons which are free, and are able to move freely within the conductor. So, examples are metals, human body, earth, and so on. And because electrons are able to move freely in these materials, if you put some charge into this, into the metal, an excess charge, then the charge gets distributed over the entire surface. Why surface? I will come to a little later. So, the metals which we use in electrical circuits, the metals, all metals are actually good conductors, and they have these electrons which can freely move within the material, and hence they are able to conduct electricity very well. Insulators, on the other hand, do not have free electrons, which can move around the material. So, they offer a high resistance to electrical currents. Example: glass, plastic, wood, etc. So, most materials that you see either fall into insulators or conductors, and when you put a charge, when a charge is put on an insulator, it stays where you put it. It stays at the same place, because it has no freedom to move from one point to another point within the material. There are another class of materials called semiconductors, whose resistance to electrical conduction is between conductors and insulators. Examples are silicon, germanium, etc. And these actually form the backbone of the electronics industry. They are also extremely important because using these semiconductors one can build many electronic devices such as transistors, diodes and so on, which form the basic component in most electronic circuits. So, having seen some basic facts about positive, negative charges and so on, we would now like to understand what are the forces between these charges, how does the force depend on the distance between the charges, how does the force depend on the magnitude of the charges, etc. So, we will start with Coulomb's law. There was a scientist, French scientist called Charles Augustin de Coulomb, who did a number of experiments in 1784 to find out how the forces between charges vary as a function of separation, how do the forces vary as a function of the magnitude of charges and so on. So, for example, he took a pair of identical charges, measured the force as a function of separation between the charges for various separations, kept separation fixed, varies the magnitude of charges, and from all these experiments, detailed experiments, he found out a relationship between the force, the magnitude of charges and the separation between the charges. So, the law is called Coulomb's law, and this is a law which tells the force between 2 point charges. Now, I must point out that point charge here implies that the size of the charge distribution is very small compared to the distance separating the two charges. So, that effectively the charge behaves like a point charge. So, if you have a spherical ball which is charged, if the size is say 1 millimeter and if you put two charges at a separation of say 100 centimeters, this charge will almost behave like a point charge. The law which I am going to write now is actually valid for point charges, and it states that the force between two point charges is proportional to the individual charges. So, let me call one charge as q1, another charge as q2, and the separation between them is r. So, the force is proportional to the product of the two charges. It is also proportional to 1 by r square, directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges, and it actually the force is along the line joining the two charges. So, if I were to write the magnitude of the force, it will look something like this, some constant q1 q2 by r square. Now, let me put a mod sign here, because as we have seen the charges can be positive or negative. So, I am just writing the magnitude of the force. So, q1 can be negative, q2 can be negative, the force could be attractive, force could be repulsive, but all the forces are described by an equation like this, and K is the proportionality constant. Proportionality constant, and if you have done gravitational forces before, this force is very similar to the relationship for gravitational force, where instead of charges you had masses, and instead of distance, the K had a certain value. So, instead of charges you had masses, and the force of gravity is always attractive, while the electrical forces can be repulsive or attractive. Now, the proportionality constant K is written as 1 by 4 pi epsilon 0. Epsilon 0 is a constant referred to as permittivity of free space. Now, in one set of units, which is the SI units, which is what we will be using primarily through the course, K is defined exactly as K is equal to 10 to the minus 7 Newton second square by Coulomb square into c square. The c, small c, this is the velocity of light in free space, and it has a definite value 2.99792.458 into 10 to the power 8 meters per second. This is now a fixed value of c. This is the value of c defined, and so if you substitute the value of c into this equation, please remember this is a unit, this is called Coulomb square, and this c is a velocity of light in free space. So, this c is defined, K is defined like this. So, I can substitute this c into this equation and get an approximate expression value for K, and that comes out to be 8.988 into 10 to the power 9 Newton meter square by Coulomb square. So, if I substitute the value of c, which I wrote here, if I substitute the value of c here into this equation, and I will get a defined value, exact value of K, and that happens to be approximately 8.998, and usually this is written as 9 into 10 to the power 9 Newton meter square by Coulomb square. So, this is the value which we will use, and the definition of the, it is in SI units, and the charges are defined in terms of Coulomb. The unit of charge is a Coulomb, which I had defined earlier, and the electronic charge is 1.6 10 to the minus 19 coulombs. Now, that was a scalar relationship between the force of attraction or repulsion between two charges. Now, let me try to, because force is a vector, I need to define the actual force between two charges. We would now like to calculate the force with direction and magnitude, because earlier what I had said was only the magnitude of the force, but I would like to also have a formula which tells me what is the direction of the force. So, for this I will start by looking at two charges q1 and q2. I have an origin here. So, this vector joining origin to q1 I will call r1 vector. The vector joining origin to q2 I will call r2 vector, and this vector is r21. So, r21 vector is r2 vector minus r1 vector. It is a vector joining q1 to q2. So, q1 and q2 are two charges, can be positive or negative. So, I will define the force on the charge 2 q2 because of the charge q1 as F21 is equal to 1 by 4 pi epsilon 0 q1 q2 by r21 square into r21 unit vector. So, here r21 unit vector is r2 minus r1 divided by magnitude of r2 minus r1. So, this is the force acting on charge q2 because of charge q1. The magnitude of the force is as we had written earlier 1 by 4 pi epsilon 0 product of the two charges divided by the square of the distance between the two charges, which is r21. So, r21 here is the magnitude of the r21 vector, and the direction of the force on q2 because of q1 is along the unit vector direction r21 joining q1 to q2. Now, this formula is valid no matter what charges you take, what the sign of the charges is. So, for example, if both charges were positive, r21 unit vector is like this, both charges are positive. So, F21 is also like this. That means the force is repulsive. Similarly, if the first charge was negative, the second charge was negative, r21 unit vector is still like this, and F21 also happens to be in the same direction, because both are negative and the force becomes positive with respect to r21 vector. So, again it is a force of repulsion. If you take 1 to be positive and q2 to be negative, r21 unit vector is still from 1 to 2, while F21 becomes oppositely directed, because one of the charges is positive, the other is negative. So, the magnitude of the force is in the direction the force is in the opposite direction to r21 unit vector, and that force becomes attractive. So, these two forces are repulsive and this is an attractive force. So, this formula is a formula which tells me the magnitude and direction of the electrostatic force between two charges q1 and q2. The force is proportional to the product of the two charges, is inversely proportional to the square of the distance separating the two charges, and is along a direction joining q1 to q2, where I am writing the force acted upon on q2 by q1. So, we will use this formula later to look at the total force on a charge in the presence of other charges. We will introduce the principle of superposition later and calculate the net force acting on a charge when more than one charge is present surrounding the charge. This force which I have written, this equation, is actually valid in vacuum or free space. If you have a medium in between, then the medium complicates because the medium also consists of charges, electrons and protons. This force law has to be slightly modified, and we will come to some discussion on electrostatics in the presence of media a little later in the course. So, that is the force acting between two charges. Let me calculate, just to give you an idea of the relative magnitude of the electrostatic forces and gravitational forces. Gravitational is always attractive, electrostatic forces can be attractive or repulsive. So, both are different kinds of forces. So, let us compare and see what is the relative magnitudes of these forces. So, let me take comparison of gravitational and electrostatic forces. So, as an example, we take two alpha particles. So, this is an alpha particle, there is another alpha particle. Now, alpha particles are actually nuclei of helium atoms. So, they have a charge of 2 e, which is equal to 3.2 10 to the minus 19 coulombs, and the mass of these alpha particles is approximately 6.64 10 to the power minus 27 kilogram. So, we take two alpha particles and they have the same charge. So, they repel each other, they have masses. So, they attract each other through gravitational force. So, let us try to compare what is the force of attraction between these, that will depend on the mass, and what is the force of repulsion between these because of electrostatic forces. That will give us an indication of the relative magnitudes of these two forces. So, the electrostatic force F e is equal to 1 by 4 pi epsilon 0 q square by r square, where q is the charge on each alpha particle and r is the separation between the two alpha particles. The gravitational force g m square by r square. So, q is the charge of the alpha particle, m is the mass of the alpha particle. G is the gravitational constant. So, we can calculate ratio of electrostatic to gravitational force, which will become 1 by 4 pi epsilon 0 g into q square by m square. The distance separating the two charges disappears from the equation. So, this ratio is independent of the separation between the two charges, whether they are close or far apart. The ratio is independent of the separation. So, now I can substitute the various values into this equation. So, F e by F g is equal to 1 by 4 pi epsilon 0 is approximately 9 into 10 to the power 9 Newton meter square by Coulomb square, divided by gravitational, this is 1 by 4 pi epsilon 0, gravitational constant is 6.67 10 to the minus 11 Newton meter square by kilogram square into q square. So, 3.2 10 to the power minus 19 Coulomb square, divided by the mass square, which is 6.64 10 to the power minus 27 kilogram square. And so, if you simplify this, this comes out to be approximately 3.1 into 10 to the power 35, an astonishingly large number. So, you can see that the electrostatic forces are much higher than the gravitational forces. With microscopic objects, the charge cancellation between the positive and negative charges is so perfect that if you have two objects like this, although there are huge number of charges in both of these objects, the electrostatic attraction is almost non-existent. There is a gravitational attraction, of course, because the masses are very small, the gravitational attraction you do not feel. You need huge masses for gravitational attraction. In fact, the very fact that we are able to stand on the earth is because of a gravitational attraction. So, the charge cancellation between electrons and protons is so perfect that in macroscopic objects, unless you charge them like we did in the experiment, the electrostatic forces are negligible. Remember that it is these electrostatic forces, electromagnetic forces, which are responsible for the atoms and molecules to join together to form solids, liquids, etc. Now, as another very interesting example, let me try to calculate what is the excess charge required to equal the gravitational attraction between two masses. So, I am going to take as an example 1 kilogram mass, another 1 kilogram mass, and separated by distance of 1 meter. So, I want to find out if these objects were neutral, there is no electrostatic attraction or repulsion, there is only a gravitational attraction. How much excess charge between these two in these two masses, assuming to be equal, will create a force which equals this gravitational attraction. So, remember that the electrostatic attraction is 1 by 4 pi epsilon 0 q square by r square. The gravitational attraction is g times m square by r square. These are magnitudes. If I want these forces to be equal, I must have 1 by 4 pi epsilon 0 q square by r square is equal to g times m square by r square, and that gives me the following equation: q is equal to square root of 4 pi epsilon 0 g into mass. So, because we have taken 1 kilogram mass, this is 6.67 10 to the minus 11 divided by 9 into 10 to the power 9 raised per half into 1 kilogram, and that is about 8.6 into 10 to the power minus 11 Coulomb. The excess charge required in each of these masses to counterbalance the gravitational attraction. I am assuming same charge, so there will be repulsion. If I want to counterbalance the gravitational attraction with charging put on the objects, then even an excess charge of about 8.6 10 to the minus 11 Coulomb will result in a force which cancels off this attractive force. Now, let me assume that these objects are made of copper. Its atomic number is 29. That means there are 29 electrons per atom, 29 protons per atom. Now, you can go back and calculate that 1 kilogram of copper contains about 9.4 into 10 to the power 24 electrons or atoms, sorry atoms. 1 kilogram of copper contains 9.4 10 to the power 4 atoms. Each atom contains 29 electrons. So, total number of electrons in 1 kilogram of copper comes out to be 2.7 into 10 to the power 26. So, these are the number of electrons, these are also the number of protons, and so the total electron charge if I multiply this by the charge per electron, I will get about 4.3 into 10 to the power 7 Coulomb. So, please note that there are so many electrons in 1 kilogram of copper, about 43 million Coulomb charges, and you need only an excess charge of about 9 10 to the minus 11. So, the percentage of excess charge required is 8.6 10 to the minus 11 divided by 4.3 10 to the power 7, which is about 2 into 10 to the power minus 16 into 100, sorry, percentage. So, I have to multiply by 100 and that is 2 into 10 to the minus 16. The percentage of excess charge required is only 10 to the minus 16 to equate the gravitational force by the electrostatic force. So, you can see the equality of charge between electrons and protons. If one of them had slightly excess charge with equal number of protons and electrons in the material, there would have been some excess charge, and that excess charge would have resulted in such a strong attraction or repulsion that they would have completely counterbalanced all gravitational forces. So, nature has produced such an equality of the charges that matter normally is completely neutral because of the exact cancellation of the electron charge and the proton charges. Yeah, I would like to leave a problem at the end of my talk for you to think about. Consider 2 point charges Q1 is equal to 0.5 microcoulomb and Q2 is equal to 1 microcoulomb placed at a separation of 10 centimeters. If the charge Q2 is increased to 4 microcoulomb, where should the charge Q2 be placed so that the force on Q1 is the same as before. One microcoulomb is equal to 10 to the minus 6